The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. The universe might not be what we thought it was. Recent discoveries from the James Webb Space Telescope are shaking up what we know about the Big Bang and the early moments of our cosmos. These findings are so mind-blowing that even renowned physicist Michio Kaku was brought to tears. Something is wrong. We may have to revise our theory of the creation of the universe. Saying that we've been lied to since 1931. What could possibly be so shocking? A new kind of space observatory. The James Webb Space Telescope, often called JWST, has captured the attention of scientists and space enthusiasts worldwide because of its remarkable power to see cosmic objects in ways we never thought possible. After more than 2 decades of development and a price tag exceeding $10 billion, JWST was finally launched on December 25, 2021 atop a European Ariane 5 rocket. Many people watched nervously as this massive observatory sporting a segmented gold-coated mirror and an enormous sunshield began its journey to a spot in space known as the Second Range Point L2. It was the culmination of years of collaboration between NASA, the European Space Agency ESA and the Canadian Space Agency CSA. Even before launch, expectations were sky-high. Astronomers worldwide believed that JWST would reveal the hidden corners of the cosmos, particularly those times right after the Big Bang when the earliest stars and galaxies took shape. Previous telescopes like the Hubble Space Telescope had already given us jaw-dropping images and impressive data about distant galaxies. Yet, many of the oldest and faintest objects in the universe remain invisible in the bandwidth Hubble uses. This is partly because as light travels enormous distances, it stretches into the infrared range due to the ongoing expansion of the universe. A process called redshift. Hubble can do some near-infrared observations, but JWST specializes in infrared, is more sensitive and can see farther into the early epochs of cosmic history. When JWST reached L2 and unfurled its mirrors, scientists had to run through a complicated process of aligning the mirrors and calibrating all instruments. A process that took several months and carried great risk. Any misstep could have ruined the mission. Fortunately, it went off without a hitch. Once the telescope started returning data, astronomers found themselves with high-resolution views of star-forming regions, chaotic galaxy clusters, and newly observed exoplanets. They marveled at the crispness of these images, with many calling it a new chapter in space exploration. However, what immediately began to steal headlines was the early glimpse of galaxies that, according to standard theory, should not exist so early in the history of the cosmos. Even right out of the gate, JWST data hinted that mature massive galaxies might have been present just a few 100 million years after the Big Bang. If confirmed, these observations would alter the classic timelines for when structures in the universe started to form. The Big Bang theory, as widely understood, holds that it took hundreds of millions of years for the earliest small stars and galaxies to form and billions of years for them to merge into large modern galaxies. Yet, some of JWST's first detections suggest a faster, more aggressive formation process than conventional models had expected. Renowned theoretical physicist Michio Kaku voiced the collective astonishment by saying that we might have to rewrite textbooks if these early findings hold up. Scientists took to social media platforms, discussing that if JWST keeps finding galaxies that mature so soon after the universe's birth, it could transform our entire view of early cosmic evolution. Many labeled the 6 ancient galaxies discovered in the telescope's initial data as strange, mysterious, or in some cases even accidental because they seemed too big, too developed, and too numerous for that epoch of cosmic time. The telescope's design and instruments. Much of JWST's power to upset established theory stems from its unique design. It has a primary mirror around 6.5 m in diameter made up of 18 hexagonal segments coated in a thin layer of gold to optimize infrared reflection. This mirror collects far more light than Hubble's 2.4 mirror, making JWST much more sensitive to faint objects. There is also a large sun shield the size of a tennis court consisting of 5 ultra-thin layers designed to keep the telescope's instruments incredibly cold. Why cold? Because infrared-sensitive instruments are so sensitive that the slightest heat from the telescope itself could blind them to the faint heat signals emanating from distant objects. Among JWST's main instruments are an infrared camera, NIRCam, to take sharp images in near-infrared light, and a mid-infrared instrument, MIRI, to identify objects glowing at slightly longer infrared wavelengths. By operating as far out as 28 micrometers, MIRI can detect dusty regions of star formation or faint distant galaxies that are heavily redshifted. Then there's the near-infrared spectrograph NAR-SPEC and the fine guidance sensor paired with the near-infrared imager and slitless spectrograph FGS-NIAS. These instruments can split incoming light into spectra, pinpointing the chemical signatures of stars, galaxies, or exoplanet atmospheres. They also help stabilize the telescope, ensuring crisp data. This technical prowess is key to understanding how anomalies arose when the first images started rolling in. The telescope's ability to see faint objects at high resolution means that astronomers can measure red shifts with more precision and detect details about star formation rates that they couldn't see before. By combining imaging with spectroscopy, they can confirm the distances of these ancient galaxies rather than relying just on assumptions. If a galaxy is indeed located at a redshift of 10 to 13, that places it no more than a few 100 million years from the moment the universe fled into being. The presence of several such galaxies would have a huge impact on how we map out cosmic history. As soon as these ancient galaxies were spotted, many astronomers worried about certain pitfall lensing effects, for instance, where massive clusters in the foreground might magnify background galaxies, making them appear both brighter and larger than they really are. While gravitational lensing certainly can happen, repeated analysis suggests that at least some of the early find galaxies are not strongly magnified illusions. Others propose that the sources might not be galaxies at all, but black holes or some other exotic objects. Yet, the data so far looks more consistent with them being bona fide galaxies packed with stars. All these findings rest on JWST's instrumentation doing exactly what it was created to do: gather pristine, detailed infrared data from objects formed at a time we've never before been able to see clearly. Each of the instruments was built to survive the stresses of rocket launch, the deep freeze of space, and a million-mile journey from Earth. Now that the telescope has shown it can do these tasks successfully, scientists are using it to study everything from distant galaxy clusters to exoplanets in our own region of the Milky Way, gleaning data that no previous instrument could so easily capture.